Hello, welcome to my Infinite Void. I'm Josh Pullen. This is my CSE 260 honors project. And the idea with the honors project is that I was supposed to pick some topic related to our class, do some research about it, create some kind of project, write a paper about it, and then present. And so this is that presentation. Now, my topic was something called symbolic execution, which is really fascinating. But before we talk about that, we should talk about why such a thing is even necessary. What problem are we trying to solve? The idea is related to testing, right? Every good computer scientist knows it's important to write tests. We should test our programs. And this is a good strategy. This works quite well. But one of the problems with testing is that you really are just testing on a finite set of possible input values, right? You have your little test suite, but it's possible that there's some error, there's some mistake in your function that you don't notice because none of your tests cover it. That's the kind of problem that we're trying to avoid. And the solution is symbolic execution. The idea with symbolic execution is that you're trying to test sort of the entire set of possible input values all at once. And the hope is that you can sort of run through the function one time and test a whole bunch of input values in one go, which sort of seems impossible until we talk about how we do it. You can see here I have this example function called main that takes two numbers and does some math, and then asserts at the end that this math must have produced a value of a and b that are equal. They must end up being the same. And so the question is, well, how do we test this? How do we sort of get the computer to know for sure? And of course, we could do the usual thing where we create some test cases. But if we really want to know that it always works, then we're going to do symbolic execution. So the idea is that rather than plugging in numbers, rather than plugging in concrete values like 4 and 8 in this case, which would give you 6 at the end for A and B, we want to plug in what are called symbolic values. And this requires having a new kind of interpreter that can handle these symbolic values. So for A, I'm going to plug in just a symbol alpha, and for B, I'm going to plug in a symbol beta. And alpha and beta sort of stand for any number, right? And so it almost seems like, well, why did you even do that? Why not just say alpha, A and B can be any number? But we'll see that this turns out to be useful. When we plug in alpha and beta, then we're going to run the line of code that says, okay, C equals B minus A divided by 2. And now what we get is that C is beta minus alpha divided by 2. So again, it seems like we've just sort of renamed these things. But then we get to the line A equals A plus C. And so now, well, A is still equal to alpha, although it's going to change soon. And C is equal to beta minus alpha divided by 2. And so A now becomes alpha plus beta minus alpha divided by 2. And this is a symbolic math expression. And we have tools, computer tools, that can manipulate these expressions. Maybe you've used Wolfram Alpha before and asked it to like simplify an expression for you. And it will go in and do this, right? It will modify these expressions. And so if you are reasoning mathematically, you can take this expression and simplify it to be alpha plus beta divided by 2, just the midpoint of alpha and beta. And then we can do sort of the same thing with B, where we say, okay, B is equal to B minus C, says, well, B becomes beta minus, well, C is this thing. And that also simplifies to alpha plus beta divided by 2. So now we have that A and B are both equal to the same symbolic expression. And so then when we go to assert that A equals B, it's like, yeah, right? That's totally true. So it's this, the concept here is that we're going to take our sort of mathematical intuitions and actually apply them and say, okay, if we can show that these things must be equal, then like we're good. We don't need specific test cases. All right, so this simple example, not too complicated, right? In particular, it's just code that runs top to bottom, right? Line 1, line 2, line 3, and then our assertion, they all just run in order. But most code is more complicated than that. And in particular, most code has branching. So things like if statements, where there are sort of conditionals and we end up following different paths through the code depending on certain conditions. So again, we're going to sort of plug in a symbolic alpha in for A. And alpha could be any number. And we're going to say if alpha is less than 0, then do the first thing. And if it's greater than or equal to 0, do the second thing. The trick here is that when we're doing our symbolic execution, the first time with this simple function, we were able to go through exactly once, basically just run the function once using symbolic values and show that the assertion was true. In this case, we're going to do what's called forking the sort of machine. And we're going to try taking both paths. So we're going to say, okay, alpha, which is the value that we give for A, it could be negative or it could be positive. And we're going to sort of split in half and consider both cases separately. So as soon as we hit this if statement, we're going to split into sort of two separate conceptual machines. The first machine is going to assume that alpha is less than 0, assume that the condition is true. And if that's the case, then it's going to hit this assertion. And because it has the assumption that alpha is less than 0, then it can look at this assertion and go, oh, that's definitely true. That works. And then this other conceptual machine is going to take the other path, right? It's not going to even look at this assert line because it's assuming that alpha is greater than or equal to 0. And so it's going to look at this other assertion and say, well, I know alpha is greater than or equal to 0, so it can't be -3, therefore the assertion is true. So this is really powerful, but it's also sort of the fundamental flaw with symbolic execution. Now, in order to talk more about the flaws, I want to show you a little symbolic execution program that I wrote myself. There's this wonderful Python package called PySMT that is very cool. It does this constraint solving where you can say, okay, here are my variables. Can you tell me, is it possible to satisfy all the requirements that I'm giving you? So the way that we use this, well, okay, first we install it. Then I've written a bunch of code here that actually does symbolic execution. And maybe we can talk about how we're using this Python package to do it. So first of all, let me just run this code here. Actually, did I run this? Yeah, I did. So this code sets up a program, and in fact it's this program here, where I'm saying, okay, I have a function with a and b where if a is less than 5, set a to equal 5, if b is less than a, set b to equal a, and then if their sum is greater than 15, set b to be b minus a. And I want to assert that a plus b is greater than or equal to 10. And it's going to turn out that actually that usually is true, but not always. So I've taken this program and essentially rewritten it in Python, but not like Python code. I've rewritten it. Essentially, I wanted to avoid creating a parser that actually like parses code. And so I've forced myself to sit here and turn this into what essentially is like something like a syntax tree, although not exactly. You can see I'm sort of cheating here. And I've also created my initial state where I'm saying, okay, plug in alpha for A and beta for B. And now I've created this code called getReachAblePaths that's basically going to do symbolic execution on this program. And so if I run this here, you can see that it tells me that there are 8 paths, 8 possible paths through the code. And let's see, 7 of them are reachable. One of them is actually like unreachable. It's like a path that maybe you think is there, but then it turns out you can't really get to. And you can see we have lots of green check marks, but we also have a couple of red X's, where there are sort of possible combinations of input values that don't work, where the assertion fails. And so in particular, it's telling me here, all right, if your beta and alpha meet these particular requirements that I've highlighted, then your assertion is going to fail. And then it gives us an example. This is where that package, SMT, PySMT, knowing how to give us examples turns out to be really useful. It says, here's an example. If A is 8 and B is 7, then your assertion will fail. And so the symbolic execution code here has successfully found a place where if you plug in these input values, the assertion fails. And so it has found an example of a failing test case, essentially, except I didn't have to write the test cases. I just wrote the code, and the symbolic execution ran through and figured out basically every possible path. But yeah, this is basically what we do. Now, it's not a problem in this case, but one of the things you might notice is, okay, there were 8 possible paths. The reason that there are 8 paths through this code is because each if statement is a choice, where you have 2 options. Either the condition is true, or the condition is false. And so if you just assume that they're all sort of independent, it's like, well, in this first if statement, you have 2 options. And then in the second if statement, you have another 2 options. And you have to multiply those to see that, okay, there's actually 4 choices already for how things can go. 4 different paths I could run through in this code. And then the final if statement doubles it again, right? It's like, okay, we got through these 2. Now, this could be true or false. I have twice as many options. Again, you can sometimes eliminate some of them if you realize that actually some aren't possible. But in general, we have to assume that you have, if we have just a big list of if statements, it's like if you have n if statements, it's going to be 2 to the power of n different paths. And so that blows up really quickly, right? If you think about, okay, if I'm writing a program, how many if statements do I have in my program? More than 3, And if I have 10 if statements, now all of a sudden I have 2 to the 10 different possible paths through the code. That is blowing up extremely quickly. And if I'm now trying to keep track of an interpreter, like a different fork, a different branch for all 2 to the 10 different possible combinations, I'm running into problems really, really quickly. And so this path explosion issue is, I would argue, the most fundamental problem with symbolic execution. The situation is even worse with loops. Here I have a little while loop. This is like the most tame, well-behaved loop ever. I'm literally setting A to 0 right away. Oh, you know what? I made a typo that I'm going to have to fix before I submit it. This, I think, is supposed to be A equals A plus 1 and A equals A plus 2. The idea here, though, is it's literally like the simplest loop ever, just about. I added an if-else, but it's really straightforward. And this causes 31 different paths to be created. Fortunately, 29 of them get killed right away because they turn out to be impossible. It does pass all the assertions. The assertion at the end that A has to be greater than or equal to 10 is true. But it took a lot of paths to get here, and this was a really easy while loop. And in fact, I was playing around with some other more complicated while loops, and I actually just crashed Google Colab I'm using. Python just toppled over. And this is really the fundamental problem that you hit with symbolic execution. So the big question is, how do you deal with the path explosion? And I think this is a case where no one solution is the perfect silver bullet. You sort of need a whole bunch of solutions all stacked on top of each other that make things, ever so slightly more efficient, step by step. So the first and sort of most obvious solution to this problem is to eliminate impossible paths. So here's my example code for this. If A is less than B, then you're inside here and you say if B is less than A. Well, you're never going to end up inside this, path. No input values will ever get you to this point in the code. And so you can just delete that path. And this is exactly what I'm doing here when I say 29 paths were killed while executing this while loop. This is the one and only optimization that I put into my code here. And the reason I did it was because if you don't do this, then every single while loop behaves like an infinite loop. So I had to put this one, unfortunately. Had to do some extra work. But this is like the first optimization you can do, is eliminate paths that are impossible. And that's a good start. Like, that really helps. It got me from infinity possible paths down to 31, 29 of which were killed. That's a big improvement. However, it's not enough. Another interesting strategy is detecting path equivalence. So here I have an example of code where we branch into like, okay, if A is less than B, then we assign C to be -1. Otherwise, we assign C to be 1. But then later on, we don't actually use C ever. C plays no role in our assertion. And so actually, it really doesn't matter which path we chose in this if-else. And so we can sort of just pick one path and just do the one. You don't even have to do the other path because you know that which path you choose is not going to impact the result of your assertion. And so, again, this is a very simple case. We're only trimming off one little path. But you can imagine a case where maybe this lets you trim off like half the paths. And if you cut your paths in half a few times, you find a few strategies that do that, suddenly you're back in business. Like, that can help quite a lot. So those are a few of the possible solutions. These are just some of the simplest ones. There's a whole world out there of people coming up with extremely clever solutions to this path explosion problem. Most of the solutions and ideas are well above my pay grade, but they're very cool, and they're worth looking into more. But in conclusion, I would say the big idea of this project is symbolic execution is extremely cool. It's a really neat idea that helps you avoid the problems with regular testing, where you might not create the test case that you need to create. And for relatively simple programs, it can be a super helpful strategy. In practice, with more complicated code, it's, there's problems, and it'll take a lot more research and a lot more effort to get to the point where this is something that we can really use in practice a lot. The good news is Microsoft actually successfully used symbolic execution while developing Windows 7 all the way back in 2008. And so this, to me, is a strong indicator that actually symbolic execution has a chance in the real world. It's like they actually used it here. Now, Microsoft is full of brilliant engineers doing some top-notch work. So it's going to take a while for these kinds of incredible strategies to sort of trickle down to the rest of us, right, sitting here in our computer science classes, but they will get there. And so my hope is that over time this becomes a strategy that's in all of our tool belts, that it's something we all can use. So symbolic execution, very cool, 10 out of 10, except it's impractical for now, unless you're very careful. But I love it a lot, and it was very fun to build this little project. So this was great.